This video describes the experiment-based concept of the inertial confrontation as the underlying mechanism of all acceleration processes. It is well established in the popular mind that when we want to accelerate a body, we must apply Newton's second law of motion. We know that the third law is associated with the process, because to every action there is an equal and opposite reaction, without a clear understanding of the mechanism underlying this law. In addition, very rarely do we consider the first law in the process. The inertial confrontation implies that all three laws of motion work together in the acceleration processes, as described here using a simple experiment. Let's start remembering the first law of motion. When a body is acted upon by an impulse, it tends to move in a straight path, with constant speed, provided the body is moving without any forces acting upon it. If the body is at rest, it tends to stay at rest, if no forces act upon it. A key point related to Newton's first law is that the rectilinear uniform motion, or the state of rest, are related to a non-accelerated reference, called inertial reference, to represent a property of matter when free of applied forces. Accelerated references, called non-inertial, imply forces and accelerations, therefore preventing the evaluation of the behavior of the bodies under the conditions of the first law. Now consider a first and a second bodies at rest. If an impulse is applied on the first body, it starts moving. When the impulse is no longer applied, its motion is uniform rectilinear. If the now moving first body is connected to a second body at rest, there is a conflict between their inertial tendencies. We are calling this situation inertial confrontation. Trying to anticipate the result of the process, we can consider three possibilities, supposing no external forces are acting upon the system. In a first hypothesis, the moving body remains moving in rectilinear uniform motion, and causes the acceleration of the body at rest. This cannot happen, because this result violates the principle of conservation of momentum and energy. That is, the momentum of the first body, moving in rectilinear uniform motion, remains constant, but the momentum of the second body increases, which renders the result impossible, since the system is closed. The second hypothesis is the motion of the first body in a circular path about the mass center of the second body, at rest. Since the rotation center, here the mass center of the second body is fixed, the uniform circular motion of the first body violates the third law of motion. However, the process does not violate the principle of conservation of momentum and energy, because the angular momentum of the first body is conserved, and the momentum of the second body is zero. However, all textbooks describe the circular motion this way. That is, the motion of a body in a circular path about a fixed center, usually attached to the Earth. This seems to be a valid procedure, because the mass of the Earth is huge. Any motion resulting from the action of a force upon it is infinitesimal and cannot be measured. Therefore, it is considered fixed for any practical purposes. However, the incurvation of the path followed by a moving body is an acceleration. A centripetal acceleration, which demands a centripetal force. If the rotating center is taken to be fixed, there is a problem to apply Newton's third law. This can be seen as one of the reasons for the idea of the centrifugal force as a reaction to the centripetal force. In other videos, this has been shown to be a misconception, because a body cannot manifest a force upon itself. In addition, the Earth seems to be fixed for observers upon its surface. They are, however, non-inertial, accelerated references. The representation of a circular motion of a body about another body at rest is applicable relative to accelerated observers, not inertial ones. Therefore, it does not correctly explain the process in accordance with the laws of motion. The circular motion of a body, forming a system with another one, can only happen about the mass center of the system. That is, when the equilibrium is established, the two bodies rotate in uniform circular motion about the mass center of the system, relative to the inertial reference, which makes the process in conformity with the laws of motion, and we can identify the pair of equal and diametrically opposite centripetal forces, causing their circular paths. The result of this experiment, implying the inertial confrontation, is the contradiction of both natural inertial tendencies of the connected bodies, It is observed that the path of the moving first body is incurvated, which implies a centripetal acceleration, while the second body, initially at rest, is accelerated. Considering that, during the interaction process, the two bodies form a system free of external forces, the acceleration of the two bodies can only be caused by the other connected body, reciprocally. The explanation for this process has been provided by Newton in the Principia, in the commentary to the definition 3, Book 1, describing how inertia is manifested. In the system of two bodies, interacting and manifesting inertial tendencies in conflict, each body causing the acceleration of the other, they manifest inertial resistances to acceleration upon each other, as reciprocal forces. Describing how inertia is manifested in a system of two bodies, Newton said, "But a body exerts this force only when another force, impressed upon it, endeavors to change its condition. And the exercise of this force may be considered both as resistance and impulse. It is resistance, insofar as the body, for maintaining its present state, withstands the force impressed. It is impulse, insofar as the body, by not easily giving way to the impressed force of another, endeavors to change the state of that other. In our example, the second body, pulled by the tendency of the first body to remain moving in rectilinear uniform motion, resists inertially, and manifests this resistance upon the first body, as a centripetal force, to cause the incurvation of its path. But the first body resists to this incurvation, which is a centripetal acceleration, and manifests this resistance as a force upon the second body, causing its acceleration. We are calling this force centripetal resistance, manifested by the first body. This is the underlying mechanism of the third law of motion. We can now see that the third law establishes the condition for the acceleration, in addition to the fact that forces are always produced in pairs of equal and opposite components. The total momentum of the system is conserved, because the first body, when causing the acceleration of the second body, transfers momentum, which means that the first body, during the process of incurvation of its path, is decelerated. This can be noted, considering that the inertial resistance of the second body acts upon the first body as a centripetal force. This vector is decomposed into two components. The component normal to the tangent to the path, at the point considered, defines the shape of the path, and a tangential component opposite to the direction of motion decelerates the first body. Now we can remember, when a body, connected to the Earth, moves in a curved path, interacts with the Earth, and an inertial conflict is established, with reciprocal effects upon each other. Although the displacement of the Earth is infinitesimal, it cannot be considered fixed anymore. Another historical misconception is the D'Alembert's principle. Taking only Newton's definition 3, without his commentary, the principle states that when a body is acted upon by an external force, it reacts and manifests a force of inertial equal and opposite. Despite the fact that this force of inertia, although equal and opposite to the applied force, does not prevent the body to be accelerated. In addition, it poses another problem that influenced the popular way of thinking on the acceleration processes. It represents the acceleration process by means of a force applied upon an isolated body, as commonly done when representing Newton's second law separated from the other laws. Without the third law fully understood, one cannot appropriately describe acceleration. In addition to the need of at least two connected bodies, acted upon by a pair of equal and opposite forces, the bodies must resist the acceleration, so that each body will act as a support for the acceleration of the other. Only after this, we can give full meaning to the resulting action and reaction pair. Two basic conditions for acceleration are stated by Newton's three laws together. The first condition is a pair of connected bodies acted upon a pair of equal and opposite forces. The second condition is the inertial resistance of the bodies to acceleration, acting upon each other. In accordance with Newton's commentary to the definition 3, Book 1, the Principia. The centrifugal force problem. In the conventional description, a body rotates about a fixed center, under the action of a centripetal force, causing the incurvation of its path, that is, a centripetal acceleration. the body reacts and manifests upon itself. A centrifugal force, in contradiction with Newton's third law. This has been shown to be a misconception, because a body cannot manifest a force upon itself. Using Newton's arguments, there is no centrifugal force. The inertial confrontation implies that all three laws of motion work together in the acceleration processes, as described here using a simple experiment. In a system of two connected bodies, interacting and with their inertial tendencies in conflict, a second body initially at rest resists acceleration, and manifests this resistance upon a first body, initially in rectilinear motion, as a centripetal force that causes the incurvation of its path, which is a centripetal acceleration. The first body resists the incurvation of its path. This resistance acts upon the second body as a force that we are calling centripetal resistance, causing its acceleration. In conclusion, inertia is resistance to acceleration, as friction is resistance to the relative motion of two bodies in contact. It is manifested when a pair of simultaneous, equal and opposite forces act upon two connected bodies, in a dynamic process described by Newton's commentary to the definition 3. Book 1, of the Principia, in conformity with the three laws of motion together, relative to an inertial reference frame.